Hi. In this video, we will introduce our paper Is the Performance of My Deep Network Too Good to Be True? A direct approach to estimating the Bayes error in binary classification. Our names are Takashi Ishida, Iko Yamane, Nantawa Kuroinfakti, Gang Miu, and Masashi Sugiyama. We are from the University of Tokyo, Riken AIP, and ENSAICREST. First, we would like to discuss the meaning of the best possible performance. For straightforward machine learning problems, we may be able to achieve 100% test accuracy, but this is not the case for most machine learning problems since we may have a non-zero irreducible error. In that case, we cannot achieve zero error, and the best possible performance is the non-zero irreducible error. Estimating the irreducible error helps evaluate the state-of-the-art performance. For example, the state-of-the-art classifier achieves 0.09% test error for the MNIST dataset and 0.50% for the CFAR10 dataset. If we can estimate the irreducible error, we can compare the SUTA performance with the estimate. Then we will be able to grasp the remaining gap between the two. In extreme cases, we may find out that the model's error exceeded the irreducible error. This may imply that test set overfitting is taking place. Knowing the irreducible error will be helpful in avoiding such common pitfalls. As shown on the right, the irreducible error can also be used as an indicator of the intrinsic difficulty of complex tasks. We will later show an example of measuring the intrinsic difficulty of the acceptance and rejection decision for scientific articles. Our paper focuses on the Bayes error, which corresponds to the irreducible error in supervised classification problems. The Bayes error, beta, can be defined as the infimum of the expectation of the 0-1 loss function. For simplicity, we only discuss the binary classification case where y is positive or negative. The Bayes classifier is the classifier that achieves the Bayes error. How can we estimate the Bayes error? There is an equivalent expression of the Bayes error without using the classifier g explicitly, shown here on the left with the red equation. The interpretation of this is that the Bayes error is the overlap between the positive and negative distributions. Intuitively, we seem to have to go through the step of estimating py given x to quantify beta. However, this is equivalent to training a classifier. Training a classifier can be considered as a naive baseline for estimating the Bayes error because a classifier will approach the Bayes classifier with sufficient training data provided that the model is correctly specified. We take a more direct approach, where we assume to have access to Ci, the probability that Xi belongs to the positive class. If we have Ci's, we can propose a simple and direct estimator beta hat. Compared with previous methods, our method is model-free because there is no model training and instance-free because instances are no longer involved. Theoretically, it is unbiased and consistent. We conduct synthetic experiments where the underlying Bayes error is known. The true Bayes error is slightly larger than 5% in this example. The true Bayes error is shown in the dotted black line in the figure. Our proposed method, shown in blue, can estimate the Bayes error accurately, even when we only have a few samples. All other baselines require much more samples to approach the Bayes error. So far, we assumed we could collect the clean soft labels Ci. However, this may be a strong assumption in practice. In our paper, we relax this and study more realistic and practical scenarios, such as noisy soft labels, multiple hard labels, and positive confidence. For noisy soft labels and sign labels, we propose beta hat noise, which is unbiased and consistent. For multiple hard labels, we propose beta tilde, which is asymptotically unbiased. For positive confidence data, we propose beta hat pconf, which is unbiased and consistent. We estimate the Bayes error for the benchmark datasets, CFAR10 and MNIST, by converting the 10 CLASS classification dataset into a binary classification problem by combining classes. For CFAR10, we use the animal classes as positive and artifact classes as negative. We construct soft labels using the proportions of the 50 human hard labels for each test image from CFAR10H and use the constructed soft label to estimate the Bayes error. The pink bar on the left figure shows how the deep network's performance has been improving over the years. However, more importantly, we can see how the test error of the vision transformer is already close to the estimated Bayes error shown in orange. For fashion MNist, we use the tops related items as positive and other items as negative. Inspired by CFAR10H, we present a new dataset called fashion MNist. This contains multiple hard labels for each test image from fashion MNist. We can see that the resonant 18S test error is already very close to the estimated Bayes error. Although there is a small gap, we believe we can reduce this further since we did not do serious hyperparameter tuning and did not add any data augmentation. We can also observe that the Bayes error for fashion MNist is higher than that of CFAR10. This is expected since the images of fashion MNist are much more ambiguous than those in CFAR10. Finally, we show how Bayes error estimation can be used to study the intrinsic difficulty of datasets such as academic paper selection difficulty. If we regard the paper selection problem as an acceptance and rejection binary classification problem, there is an underlying Bayes error that we would like to estimate. We use the weighted average of the ICLR reviewers' scores based on the confidence provided by the reviewers. We further calibrate this so that we can use this as a soft label. See further details in our paper. The right table shows the results, and we can see that the Bayes error is between 6% and 10%. This is much higher than CFAR10 and fashion MNist. This is expected since understanding a paper's value and significance is much more difficult than recognizing cats and t-shirts. We can see no disruptive changes by comparing the Bayes error between different years. For example, Bayes error is not doubling or tripling. This real-world experiment demonstrates the benefit of our instance-free approach. It is non-trivial how we should train an accept-reject classifier, but we can easily estimate the Bayes error without using textual information from the paper itself. To summarize, we can estimate the Bayes error in an instance-free and model-free fashion with soft labels. We also show uncertainty labels, noisy soft labels, multiple hard labels, or positive confidence can be used. We demonstrate how the test error of recent deep networks are already very close to the Bayes error with CFAR10 and fashion MNist. Although we did not detect strong evidence of test set overfitting, we are interested in investigating other benchmark datasets in the future. We also show how this can be used as a tool to study datasets by estimating the Bayes error of ICLR papers as an example. If you are interested in the details of this paper or the implementation, please check our links shown here. Thank you for your attention.